This is lesson number 2 for engineering dynamics. In this video we will look at curvilinear motion and projectiles. The tutorial contents includes an introduction to curvilinear motion and the rectangular coordinate system. We will look at projectiles and the derivation of all the equations that we need, and then we'll complete 3 example problems for you to have a look at. So let's continue on. So what I have here is the particle which is constrained to move along this curved path. And the shape of that path is defined by the function s equals s of t, where s is just the position along that curve at any instant in time. So one way we can define the position of that particle is just by the distance s it is along that curve. And that would give us a scalar quantity. And the other way is to use a quantity called r, which is measured from the fixed point O, and that is a vector quantity shown by this arrow on top. Okay, so that is the other way to define its position along the curve. So let's say now the particle moves from the position r down to the position r prime, where r prime is also measured from the same fixed point O. So the change in position would give us delta r, where again delta r is a vector quantity. Now when the particle moved from this point here r down to the point r prime, it also covered a distance along that curve, which I'm going to call delta s. Now it's important to know that delta s and delta r have very different lengths. So delta r is literally the particle moving straight from that position down to there, but delta s is the path that is taken along the curve to get to the same position. You have to be aware that delta r is a vector quantity and delta s, we're going to say that's a scalar quantity. R prime would just be r plus delta r. So if we wanted to know what the new position r prime is, we just add r and delta r together and we get r prime. Or if we want to find the difference in position, so if we want to find delta r, we just do r prime minus r. So now let's talk about velocity. So when the particle moves from position r to position r prime in a time delta t, we can use that information there to find the average velocity from when the particle moved from this position to that position. So that is shown by this equation here. So we have delta r divided by delta t, and then if we take the limit as delta t approaches 0, we get the instantaneous velocity, which we call big V this time, with a little arrow on top showing us that it's a vector quantity, and that is equal to dr by dt, which is equal to r dot, remembering that dot notation there. And that will give us the instantaneous velocity. The other way we could find velocity is if we take delta s and delta t, and then we use those two there to find the velocity, and then take the limit as delta t approaches 0, we get small v. So small v is going to be a scalar quantity because remember delta s was a scalar, and that would give us ds by dt, which equals s dot. So s dot is just the time rate of change of distance along the curve, and r dot is the time rate of change of the vector position of the particle. So what we can draw from this is that the magnitude of v, so the magnitude of big V there, is equal to small v. So remember the magnitude, and that is going to be equal to ds dt. And we can also say the magnitude of r dot is equal to s dot. Okay, so if we now have a look at acceleration in curvilinear motion, and we have our particle located here at position r from the fixed point O, and this is at time t, and then it moves along that curve to this position here, we're calling r prime from the fixed point O, and that is at time t plus delta t. Okay, so the velocity of the particle at this point here we're calling v, and the velocity of the particle at this point I'm calling v prime, where v prime is equal to v plus delta v. So if we take these two velocity vectors and connect their tails together, and we draw in delta v. Okay, so this arrow here was v, this arrow here was v prime, and then we just drew in delta v there. Okay, so you can see delta v is acting towards the concave side of the curve, and if we was to write the average acceleration, we would just do v prime minus v divided by t plus delta t minus t, where the t's there cancel out to give us delta t on the bottom here, and v prime minus v is delta v. So this is the average acceleration. So if we take the limit as delta t approaches 0 for delta v by delta t, we get a, which is also equal to dv by dt, which is also equal to d2r by dt squared. So the second derivative of the vector positions of the particle. So the acceleration a includes the effects of both the change in the magnitude of v along that curve and the change in direction. Okay, so since it's accelerating along the curve and its position has changed, that means a is going to include the effects of both its increase in velocity along the curve and its change in direction. So that means from this we can see that acceleration a acts neither tangent to the path or normal to the path. So the acceleration, so the change in magnitude of v occurs along the path, and there's another acceleration which occurs because of the change in its position. If we was to draw in a, it would look like this. Okay, so it's acting towards the concave side of the curve, so it's neither tangent to the path or normal to the path. So what's important to know from this is that acceleration a has two components. So okay, there's one component that acts tangent to the path, and there's another component that acts towards the center of curvature. And if you take the resultant of those two accelerations, you'll get a. We will look at this in more detail in the next tutorial, but for now we're just going to say a acts towards the concave side of the curve, and that's all we need to know for now. Another important thing to note is that if the velocity along the curve was constant, so there's no change in magnitude of velocity, that would mean a would act towards a center of curvature. Now a common mistake is to think that if the velocity was constant, the acceleration would act normal towards the vector position r, but it wouldn't. Okay, it acts towards the center of curvature. Another thing to make clear is that velocity is not tangent to the vector position r, it is only tangent to the path. Okay, so now we've completed our introduction to curvilinear motion. Now we're going to look at the rectangular coordinate system. The rectangular coordinate system consists of x and y axes. So there's the x-axis there, and there's the y-axis there. There are also two unit vectors in the direction of each axis. So there's the r unit vector and the j unit vector. So by unit vector we just mean the vector has a magnitude of 1. So let's draw our arbitrary curve in our rectangular coordinate system, and the distance along that curve is just s. If we have our particle here located at the position r, and then if that moves along the path it's at another position r, and that's how r changes as the particle moves along the path. So if we just focus on this position now, we can define the position r, okay, in terms of its x distance and its y distance. So there's this x distance there and the y distance there, and the way we'd write this in vector form would be like this. So r equals x times the unit vector I plus the y times the j unit vector. So that's how we write that in vector form. Okay, and to find the magnitude we just apply Pythagoras to that. You can see how x and y change as the particle moves along that path. Now let's talk about velocity. If the particle starts at this point here, moves along that path to this point there, and it does that in a time delta t. Okay, so delta t is just the time elapsed from when it started moving from this point to that point. We can define its new position there as an x distance and call that x prime, and a y distance we call y prime. So the change in y, delta y, is just going to be y prime minus y. The change in x is going to be x prime minus x, and we're going to call the position there r prime. So to find dr dt, which is the velocity of the particle at this point, we will get r prime minus r divided by delta t. So we take the change in position and we divide that by delta t. To find that change in position of r prime minus r, we subtract the I components from both positions. So we subtract the I component of r prime by the I component of r. So we do x prime minus x, and we do the same thing for the j component. So we do y prime minus y over delta t, and that will give us the average velocity. So if we take the limit as delta t approaches 0 for delta x by delta t, remember delta x was just x prime minus x, we get dx dt, and we can write dx dt as vx, or we can write that as x dot. Do the same thing for delta y, so we take the limit as delta t approaches 0 for delta y by delta t, we get dy dt, where we can rewrite dy dt as vy and as y dot. So the way we'd write the velocity would be like this. So we'd have dx dt in the I direction plus dy dt in the j direction. We can also write that like this. We can also write it like this as well. The magnitude of v equals small v, which is equal to the Pythagoras of vx and vy. And we can also say the rate of change of distance along the curve is going to be ds dt, which also gives us small v. and we can say the magnitude of v, so big V there, equals small v, which is equal to ds dt. And we can also say the magnitude of r dot equals s dot. So let's say we're given the position of the particle, and at this particular point it's got a velocity, and we're asked to find what angle that velocity vector here makes with the x-axis. What we do from there is just take the velocity in the y direction and the velocity in x direction, plug them into this equation here, so inverse tan of Vy by Vx, where Vy is the opposite to that angle and Vx is the adjacent. We can just apply this and we can get the angle between V and the x-axis. So let's have a look at an example. So a particle is moving on the xy plane, which has x and y coordinates that vary with time. So it varies with time according to these two functions here. So x equals 5 meters minus 0.25 meters per second squared times t squared, and y equals t plus 0.05 meters per second squared times t squared. So we need to find the coordinates and distance from the origin at time t equals 4 seconds. We need to find the displacement and the average velocity vectors for the interval t equals 0 seconds to t equals 4 seconds. We need to find the general expression for the instantaneous velocity vector v and express v in component form and in terms of direction and magnitude at time t equals 4 seconds. Let's do the first bit. So we take our functions there, and then we just plug in 4 seconds into both. Okay, so I just replaced t there with 4, t there with 4, and t there with 4 as well to get this. So I get x equals 1 meter and y equals 3.2 meters. So these are the x and y positions of the particle at 4 seconds. Okay, so let's find the distance. So we just find the magnitude of r. So r equals x squared plus y squared square rooted, which gives us that. So we just put in x into there, put y into there to get this. And then that simplifies to just 1. And that simplifies to 10.24. Add these two, take the square root, and we get 3.35 meters. So now we want to find the displacement and average velocity vectors from the interval between 0 seconds and 4 seconds. So let's take our positions when time t equals 4 seconds, and then we plug in 0 seconds into our original function to get this. So x equals 5 meters and y equals 0 meters at time t equals 0 seconds, so we leave that to one side there. To find the displacement, we just do I equals x times I plus y times j. We apply this formula, and this is at 4 seconds. Okay, so I've just written this in vector form at 4 seconds. This is at 0 seconds. Okay, so the subscript is telling us the times, and then we find the difference between them. So we do r sub 4 minus r sub 0. So we do 1 minus 5, which gives us minus 4, and we do 3.2 minus 0, which just gives us 3.2. Now we want to find the average velocity. Okay, so that's just going to be delta r by delta t, which gives us v average. We know it's going to be r sub 4 minus r sub 0 divided by delta t, which will be minus 4 plus 3.2 over delta t, which is 4 minus 0, which will just give us 4. Okay, so delta r by delta t, that will just simplify down to minus 1, because we've got minus 4 divided by 4, which gives us minus 1, and then 3.2 divided by 4, which gives us 0.8. So that is our average velocity in vector form. So now we're going to use this general expression there for our function. Okay, so we've got x as a function of t, and we've got y as a function of t there. It's shown by these. So x is a function of t, y is a function of t. Substitute those in. So I just substituted x of t with our function there, and y of t with this function. So now I want to find the instantaneous velocity. So I take the derivative of this to get dr dt, which will be dx dt in the I direction plus dy dt in the j direction. So I perform the derivative. So the derivative of 5 is going to be 0, and then differentiate minus 0.25 times t, which will just give me minus 0.5 times t. So I just bring the exponential down by 1, multiply it by its original exponent. Do the same thing here. So the derivative of t is just going to be 1, and the derivative of this will give me 0.1 times t. And then I substitute time t is 4 seconds into there and into there to get this, and then simplify that down with my calculator to get dr dt as minus 2 meters per second in the I direction plus 1.4 meters per second in the j direction, and that is the instantaneous velocity written in vector form. Now I'll find the magnitude of that to get v equals small v, which equals vx squared plus vy squared, and then square rooted, which will give me this. So I just substitute the values into there. So vx was minus 2 meters per second, and Vy was 1.4 meters per second, so I'll substitute those into here to get this. and that simplifies down to square root of 5.96, which gives me 2.44 meters per second. Okay, so now I want to find the directions. So the velocity direction, that's going to be theta equals inverse tan of Vy by Vx. So I'll substitute my values in, so I knew Vy was 1.4 meters per second, Vx was 2 meters per second, substitute those in, and then that's going to simplify down to inverse tan of minus 0.7, which is minus 35 degrees. So if we look at acceleration now, if we have the particle at this particular point now along this curve S, and it's got a certain velocity v, noting that the velocity vector at this point is tangent to the path, and if it moves from that point to this point, and it's got a new velocity v prime, again noting that the velocity vector at this point is tangent to the path, and it moves from this point to that point in a time delta t, we can find the change of velocity in the I direction and the change in velocity in the j direction. And we can write the average acceleration as delta v by delta t, which will be v prime minus v over delta t, and then we do the vector subtraction between v prime and v, because remember v and v prime are vector quantities, so we just subtract the components of velocity in the I direction and the components of velocity in the j direction, and that will give us the average acceleration. And if we take the limit as delta t approaches 0 for delta v sub x over delta t, we get dvx by dt, and then that can also be written as ax or v dot sub x. And if we do the same thing for the change of velocity in the y direction, so take the limit as delta t approaches 0 for delta v sub y over delta t, we get dv sub y over delta t, and then dv sub y by delta t can be written as a sub y or v dot sub y. And we write that in vector notation like this, so we got a equals dv sub x by dt in the I direction plus dv sub y by dt in the j direction, and we can also write that like this, and we can also write it like this. We can then find the magnitude of a by just applying Pythagoras to ax and ay. So if we apply that, we get the magnitude shown by these two vertical lines here, and that will give us small a. Also noting that ds dot by dt equals a, so that is the acceleration along the path. If we also note that if the particle moves on a curve, the acceleration vector a always points towards the concave side of the curve. Acceleration is only tangent to the path if the particle moves in a straight line. The acceleration acts towards the concave side of the curve shown here. So let's have a look at another example. A particle is moving on the xy plane which has x and y coordinates that vary with time according to x equals 5 meters minus 0.25 meters per second squared times t squared, and y equals t plus 0.05 meters per second squared times t squared. Find the components for the average acceleration for the time interval t equals 0 seconds to time t equals 4 seconds. Find the instantaneous acceleration vector a and express a in component form and in terms of the direction and magnitude at time t equals 4 seconds. So let's take these two functions there. Here's our general expression for r, where x and y are varying with time. So we have x of t in the I direction and y of t in the j direction. Here's x of t and here's y of t there. So substitute those in, and now we want to find the instantaneous velocity v at time t equals 0 seconds. We get this, okay, so d sub 0, where 0 it means time t equals 0 seconds, by dt equals dx dt in the I direction plus dy dt in the j direction. So take those derivatives. So derivative of this would be that, and the derivative of that is this. Substitute time t equals 0 seconds into there, and we get this. And then we can say Vx equals 0 meters per second, and Vy is 1 meters per second. So put them to one side. Okay, so we do the same thing again, but we evaluate t with 4 seconds. Okay, so dr sub 4, that just means we're evaluating v at 4 seconds. Same thing again, but substitute time t equals 4 seconds into there, and we get this. And we can say Vx equals minus 2 meters per second, and Vy is 1.4 meters per second. So we'll store those. Okay, so to find the average acceleration, we say a sub av dash x equals delta v sub y over delta t. It's going to be minus 2 minus 0, so minus 2 minus 0 by 4, because 4 minus 0 will just give us 4, which will give us minus 0.5 meters per second squared. Do the same thing again in the y direction, so a sub av dash y is delta v sub y over delta t, which is 1.4 minus 1, so 1.4 minus 1 by delta t, and that will give us 0.1 meters per second squared. And then we can take that and write that in vector notation. So the average velocity is minus 0.5 meters per second squared in the I direction plus 0.1 meters per second squared in the J direction. So you can see the acceleration is actually constant. It's decelerating in the I direction and accelerating in the J direction. So now let's find the instantaneous acceleration. So the instantaneous velocity is going to give us this. Okay, we've already seen that before. And then we take our derivatives for our function, we get that. Then the instantaneous acceleration is going to be d by dt of dr dt, so we're just differentiating again. Okay, and we get d by dt of dx dt in the I direction plus d by dt of dy dt in the j direction. We get a written like this. Okay, so this is just the second derivative, so this is just this expression here rewritten like this. And then if we take those derivatives, we get minus 0.5 meters per second squared in the I direction plus 0.1 meters per second squared in the j direction. And this would be our instantaneous acceleration. Our instantaneous acceleration and our average acceleration that we found previously. And from this we can say ax equals minus 0.5 meters per second squared and ay is 0.1 meters per second squared. And then we find the magnitude of a, and we just apply Pythagoras to that, and then we get this. So we substitute our values in. So ax was minus 0.5 and ay was 0.1. Simplify all that down, we get 0.51 meters per second squared. So this is the magnitude of the acceleration. And the direction would be inverse tan of 0.1 over minus 0.5, which is inverse tan of minus 0.2, and that would give us minus 11.31 degrees. So that would be the angle it makes, but with the minus x-axis. Okay, so let's have a look at the particle's motion in 3 dimensions. Now I've added a new coordinate axis called z, and a new unit vector I've called k, which acts in the direction of z. Okay, so the particle, to get to this position, it's just moved a certain amount in the I direction, the j direction, and the k direction. We write the position of the particle r as x in the I direction, so there's the distance there, x, and that's in the I direction, plus the distance along the y direction, which is this distance here, and that is in the j direction, plus the z distance it's covered, and that is in the k direction. So that is r written in vector notation in 3 dimensions. So let's say that the particle moves from this position to a new position there, okay, and it's followed this path to get to that new position, okay, and it's done that in a time delta t, and we say its new position there is going to be r prime, and we can write r prime like this. So x prime, the I direction, so x prime would be this distance here, y prime would be that distance over there, and that's in the j direction, and z prime would be this distance here, and that's in the k direction. So if we find the difference between the two to get delta r, we do r prime minus r. So we do x prime minus x for the I direction, and then y prime minus y for the j direction, and then z prime minus z for the k direction. And then if we divide that by delta t, we get the average velocity in vector form. If we continue on there, and then if we take the limit as delta t approaches 0, we get the instantaneous velocity. So if we take the limit as delta t approaches 0 of delta r by delta t, we get dr dt. So that is equal to d by dt of x with respect to time, and d by dt of y, and d by dt of z. We can equivalently say, if we know x, y, and z as functions of time, we can write it like this. Okay, so we take the derivative of x as a function of time, y as a function of time, and z as a function of time. So if we take the second derivative now, we'll get the acceleration. Okay, the instantaneous acceleration, provided we know the function of x with respect to time, y with respect to time, and z with respect to time. So this expression here is making the assumptions that I, j, and k are fixed. Okay, so if I, j, and k are not fixed, which means this whole coordinate system would be changing and moving around, I, j, and k would then become functions of time. Now, if that particle is still moving inside that x, y, z coordinate system, and I, j, and k aren't fixed, but they're still connected to the origin, but they're just not fixed, they become themselves functions of time. Now, they still have a magnitude of 1, okay, but their directions would be changing, and that's what would be changing with time. Okay, so if that condition exists, we would write it like this. I is now a function of time, j is a function of time, and k is a function of time as well. So if we was to perform our derivative here, because we've got 2 functions of time, we've got x of t and I of t, in each direction, so we've got y of t there, j of t there, z of t, and k of t, we'd have to apply the product rule to that. Okay, so the product rule just involves taking the derivative of the first function, leaving this other one alone, plus the derivative of this function, and then leaving this one alone. Okay, so if we do that for each one, we'd end up with this. So we've got dx dt, and then I of t was left alone, and then we've got di dt times x of t, and then the same thing was applied to this, and the same thing was applied to that. Okay, so this is the expression we get if I and j are not fixed and they become functions of time. We will look at this motion later on, but for now we're going to say I, j, and k are fixed, which means their derivatives would be 0. Okay, so they become 0. So these terms would disappear. So this term goes, that term goes, and this term goes. Just get left with this. The same thing applies for acceleration as well. So you can imagine if we was to take the other time derivative of this, we'd get an even longer expression, so it can become quite confusing, but we will look at this at a later stage. Okay, so let's have a look at an example. A particle is moving in all 3 dimensions starting from the origin. The vector position of the particle varies with time according to r equals t squared meters in the I direction plus 4t squared meters j plus 6t meters k. Find the coordinates and distance from the origin at time t equals 4 seconds. Find the general expression for the instantaneous velocity vector v. Express v in component form and find its magnitude at time t equals 4 seconds. And find the general expression for instantaneous acceleration vector a. And express a in component form and find its magnitude at time t equals 4 seconds. So let's do the first part. So we need to know our function, and our function was this. So x of t was t squared, y of t was 4t squared, and z of t was 6t. So we put in time t equals 4 seconds into there to get our positions at 4 seconds, and that will simplify down to 16 meters in the I direction, 64 meters in the j direction, and 24 meters in the k direction. So that is our coordinates. The magnitude of r, we just apply Pythagoras to that, put our numbers in. So remember, x was 16, y was 64, and z was 24. And then it simplifies down to this. Take the square root, and we get 70.2 meters. And that is the answer to this part. So there was our function there. So find the general expression for the instantaneous velocity vector v, and express v in component form, and find its magnitude when t equals 4 seconds. So the general expression for the instantaneous velocity vector, so we know dr dt is going to give us v, so we just differentiate this lot, so we get 2t meters per second in the I direction, and then 8t meters per second in the j direction, 6 meters per second in the k direction. Okay, so that is our general expression for the instantaneous velocity vector v. Okay, so we put in time t equals 4 seconds, and we get this. And then if we find its magnitude, we just apply Pythagoras to this, and then we put the numbers in, and then we get square root of 1124, which is 33.53 meters per second, and that is the magnitude at time t equals 4 seconds. So find the general expression for the instantaneous acceleration vector a, express a in component form, and find its magnitude when time t equals 4 seconds. So there was our function there, and here was our general expression for velocity. So to get acceleration, we just take the derivative of that, and we get 2 meters per second squared in the I direction, 8 meters per second squared in the j direction, and 0 meters per second squared in the k direction. And it's just going to simplify down to this. So that means our acceleration is just going to be 2 meters per second squared in the I direction and 8 meters per second squared in the j direction, and it's constant. Now we find the magnitude of a. Again, we apply Pythagoras to that, put our numbers in. So ax was 2 meters per second squared, ay was 8 meters per second squared. Add these together to get the square root of 68. And then we find the magnitude of a is 8.2 meters per second squared. And that completes this problem. Now that we've looked at curvilinear motion and the rectangular coordinate system, we're now going to look at projectiles. So in this section here, I'll be working just with symbols, as it can be quite useful for you to see where the equations come from, and hopefully along the way you'll pick up some mathematical tricks. And in the last section here, we'll look at 3 numerical examples for you to have a look at. So what I have here is a particle located at the origin in our rectangular coordinate system, and it's being released here with a velocity shown by this green arrow in the direction theta sub 0. And that would mean that the velocity is then going to have two components. So a component in the I direction, which I'm calling v sub 0 x, and a component in the j direction called v0 sub y. When the projectile is released, it's going to follow this sort of motion. So you can see here that the velocity in the j direction is actually decreasing. And then when it gets to the very top, its velocity is going to be 0, but the velocity in the I direction remains constant. And when it gets to the top, it then changes direction, so it goes downwards. So this time it's picking up speed in the y direction, and then it hits the bottom. So you can see the whole time when the particle is launched from this point and following this path, its velocity in the j direction was decreasing up to this point, so it was 0 at this point, and then it started increasing again when it hit the bottom. Acceleration in the j direction is just a sub y, which is minus g, where g is minus 9.81 meters per second squared. So that is the acceleration due to gravity, and that only occurs in the j direction, so vertically, which is why the particle starts to decelerate in this portion here, and then starts to accelerate in this portion there. So we can also say that a sub x is 0 meters per second squared, so there's 0 acceleration in the I direction, so horizontally there's no acceleration, and we can say v0y is v0 times sine theta sub 0, okay? And the velocity in the I direction is going to be v0x, which is v sub 0 times cos theta sub 0. So this is the acceleration in the I direction, so it's 0. This is the velocity in the vertical direction and velocity in the horizontal direction. So as a little exercise for yourself, why don't you pause the video now and grab yourself a bit of pen and paper and draw what you think the velocity time graph would look like for this projectile motion in both the horizontal and vertical directions. So I'm going to draw my velocity axis. Okay, remember velocity is a vector quantity, so I've got positive v there, negative v down here, and then I'm going to draw my time axis. Okay, that's my time axis. So in the horizontal direction, my velocity is going to be constant, and that's going to be positive. So in the horizontal direction, my velocity is just constant, so I would draw it like this. And the velocity in the vertical direction is going to be changing, okay? But I know the acceleration is constant, so that means the gradient is going to be constant. So it's going to be a straight line, okay? So it starts off with positive velocity down here. So it starts off with positive velocity there, and then as it's going up, it's decreasing at a constant rate. So it's going down at a constant rate, and then by the time it gets to this point where it's 0 at the top, it then goes down but in the opposite direction. Okay, so it's going to continue on down here, and then eventually it gets to 0 down to this position down here. Okay, so these were the equations that we got from rectilinear motion in the previous video. So if you're not already familiar with these equations, then I recommend you watch that video and then make note of these equations, because we're going to use these now to describe our projectile motion. So if we take our projectile here, we're going to describe the motion in the horizontal direction. So we're going to use our first equation from rectilinear motion, and then we're going to replace v with v sub x, which is the final velocity in the x direction, which is equal to v sub 0x, and that is because acceleration is 0, so this whole term here disappears. And then we can just rewrite this like this, okay? So if you remember that v sub 0x was v0 times cos theta, and then we'll apply our other equation here. So again, acceleration is 0, so this term is going to disappear. And we can rewrite this as x equals x sub 0 plus v sub 0x times t. And so all I did was just replace v sub 0x with this. And then we can apply our final equation here. This whole term is going to go because acceleration is 0. And we're just going to get left with this. And then we can rewrite that like this again. So now we'll look at motion in the vertical direction. So again, we take this equation here, and then we replace v with v sub y, which is equal to v0y minus gt, because this time the acceleration is going to be the acceleration due to gravity. Okay, so I just replaced a there with g, and we can rewrite it like this. So again, making those substitutions in, so I substituted v sub 0y with this here. And then if I apply my other equation, I get this. Okay, so I've replaced position s with y, so that's our y position, initial y position. Okay, so now if we apply our other equation, which is v squared equals v0 squared plus 2a times s minus s0. We apply it like this. So this is our equations in the horizontal direction, and these are our equations in the vertical direction. So I'd make note of these because we're going to be using these quite regularly. So if we now talk about the path of the projectile, so if we take our equations that we had for the x position and the y positions, we'll just say x0 is 0, and we'll just be left with this. And then if we say y0 is 0, we'll just be left with that. So if we take these two equations now, rearrange this equation for time, and then substitute that into here. So I'll substitute this into there and there to get this. And then what I see from here is that the V0s cancel out. Okay, so this V0 there and this V0 will cancel out, leaving behind this. And then if I just bring this squared into the bracket like this, I can then rewrite sine theta over cos theta as tan theta. And then finally I can rewrite this equation like this by just bringing the 2 down here and the g on top. And then I can bring out the x squared, and I'll be left with this equation here. So I'm going to say b is equal to tan theta, and I'm going to say c is equal to g over 2 times v0 squared times cos theta squared. And then I can write that in a more compact way like this. So this equation here describes the path of a parabola. Okay, so this is a function, and if we were to plot this on a software like, let's say for example Wolfram Alpha, if I just set b and c to 1, okay, so that's my input there, so I'll just set b and c to 1, and if that gets plotted it looks like this, so it takes this parabolic path like that. Let's find the flight time for the projectile. So when the projectile was launched from this position here, after flight has occurred, it's going to end up at this position there. So if we look at its position in the y direction, it starts off from this position here and then ends up there. So that means its displacement in the vertical direction is going to be 0. Okay, so the displacement in the y direction is going to be 0. So if we apply this equation now and we set y as 0, we then subtract both sides by this and then multiply both sides by -1, we'll end up with this. And then that t cancels out and that squared goes, leaving behind this. And then if we divide both sides by g and times both sides by 2, we'll end up with this equation here. Okay, so that is our equation for the time of flight of the projectile. What angle would give the maximum flight time? So the angle would be 90 degrees, and that is because sine theta is going to be a maximum when theta is 90 degrees. Okay, so when this is at 90 degrees, so in other words, if the projectile was launched vertically, that would give the maximum flight time. Let's find the maximum height of the projectile. Okay, so there's the maximum height, so it's located at that central point there along the parabolic path. And when it reaches that point, the velocity in the y direction is going to be 0, because that's going to be the point where it stops momentarily and then changes direction and goes the other way. Okay, so when the projectile reaches the maximum height, v sub y is going to be 0. So if we apply this equation and then rewrite it like this, okay, and then bring it down here, we can set v sub y as 0, and then I'm going to rewrite t there as t sub y max, which is the time taken to reach that maximum y distance. And then if I subtract both sides by this and then multiply both sides by -1, I'll end up with that. And then if I divide both sides by g, and then if I apply this equation now, and then I'm going to rewrite y as y sub max, because this is our maximum height in this direction. And then I'm going to rewrite t there as t sub y max, and this t there as t sub y max, okay, because this time and this time are going to be the same. And then if I substitute t sub y max into here and here, I end up with this. And then if I bring the square into the brackets, and then I see v sub 0 times v sub 0 can be written as v sub 0 squared, and then sine theta times sine theta can be written as sine squared theta. This g is going to cancel out, and the squared there is going to go, leaving behind this. And then if I factor out v sub 0 squared times sine squared theta over g from both terms, I'll end up with this. And then the 1 minus a half is going to simplify to a half. And then if I bring the 2 into there, I'll be left with this. So that is our equation for the maximum height. What angle would give maximum height? Again, that's going to be 90 degrees, because sine theta is maximum when it's 90 degrees. So if this was launched vertically, it would give the maximum height, which physically makes sense. So let's find the maximum range for the projectile. So after flight has occurred in time t, the maximum range of the projectile is covered when distance y is 0 when it hits the x-axis. So again, the displacement in the vertical direction is going to be 0. Okay, so this is going to be quite simple to do. So all we need to do is just find the constant velocity v sub 0 x and then multiply that by the overall time of flight to get the range. The velocity in the horizontal direction is going to be constant, and then I can just rewrite that like this, and then I can say r sub max, where r sub max is the range of the projectile from this point to that point, and I can just say that's the velocity in the horizontal direction times the time of flight. And remember, the time of flight, we found that earlier on. So if we just substitute that into here, we get this, make our simplifications, and then we can rewrite that like this, and then we can rewrite this whole lot here like that using trig identities. So that is our equation for the range of the projectile. So what angle would give the maximum range? Because we've got a 2 there, the angle would be 45 degrees. So if we put in 45 degrees into there, we'd end up with sine 90. And remember, sine theta is going to be a maximum when theta is 90 degrees. So to make this 90 degrees, we'd have to put in 45 degrees into there. So the angle that would give maximum range would be 45 degrees. Okay, so let's say the projectile was launched from a height this time. Okay, so it's launched from this point and then it does that motion there. Okay, so we're going to call that height y sub 0. Okay, and that was the path that it took from that point when it was launched. Okay, so these are the equations that we found earlier on for the time of flight of the projectile and for the maximum vertical distance that it covers. And we can split this up like this. Okay, so we can imagine from this point it just done its regular trajectory that we've seen before, and then we can draw in the maximum y distance there. Okay, so what I'm going to do now is actually take this equation, divide it by 2, because I want to find out the time taken to go from this point here up to that point, and that's only half of the flight for this section here. So I'll just divide that by 2 to get this. So that's t sub y max. So t sub y max is the time taken to cover this distance here in the vertical direction. So next we need to find the time taken to reach the ground from y sub max. Okay, so we need to find the time taken for the projectile to go from this point down to the ground. So for that I'm going to use this equation where I'm going to say the final position is going to be y. Okay, so the final position is going to be this distance here along the y direction, and the initial direction I'm going to call y sub 0 at y max. So this is the initial y position at this point here at y max. And then I can say y, the final y position, is equal to y max plus y0, because the final y position from this point is going to be that distance plus y0. So that is its final position there, and its initial position y sub 0 at y max is just going to be 0. Okay, so I'm going to set that to 0. And then the initial velocity in the y direction, so v sub 0 y, I'm going to say that's 0 because remember when it got to this point the velocity was 0 in the vertical direction. So I can set that as 0 down here. And notice this time I've put the acceleration as positive because it's accelerating from this point. So when it falls from that point, it's actually accelerating downwards with 9.81 meters per second squared. And I'm going to rewrite t there as t sub ground, which means the time taken to go from this point to this point. So then that is just going to leave me with this. So now what I can do is substitute y sub max into here to get this. And then what I can do is multiply everything here by 2. So the 2 is going to cancel there. That's been multiplied by 2 down here. So this half is going to go as well to leave behind this. And then what I can do is divide everything by g, okay, to get this down here. So I divide this side by g, the g is going to cancel. So that divided by g to get this, and then that divided by g to get g squared. And then take the square root of both sides. So now I've got the time taken to go from y max to the ground. So the total time, so t sub total is going to be t sub y max plus t sub ground, and that's going to give us this. Okay, so I'll substitute ty max into here to get that, and then substitute this into here to get that. And then I can rewrite this term like this. And that is the time of flight for the projectile. Okay, so if we take our equation there for flight time, and let's say we wanted to find what the velocity, initial velocity that the projectile was launched with, let's say if we wanted to find that, and we want to rearrange this for v sub 0. So this could be quite a tricky procedure, but I'll take you through it now. So we want to rearrange this for v sub 0. So what I can do first is subtract this term from both sides to get this term down here. Okay, so t sub total minus v sub 0 sine theta over g. Subtracted that from both sides to get this. And then I can square both sides by getting rid of this square root. So I'll square this side, square that side. And then I can rewrite this term like this, because this is just the whole lot here, then inside the brackets being multiplied by itself. So I can rewrite that like this. And then if I expand those brackets, so I do t subtotal times t subtotal, and then multiply t subtotal by this, and then multiply this term by that term, and this term by that term, I end up with this expression down here. Okay, so I just expanded these brackets. Okay, that term's going to cancel out, and that term's going to cancel out because they're on both sides, and it's just going to leave us with this. So then if I add this term to both sides, so minus 2 times t subtotal times v sub 0 times sine theta over g, add that to both sides to get this, and also subtracted this from both sides to get this here. And then what I can do is divide both sides by 2 times t subtotal to get this, so I just divided both sides by this, I end up with that. So if I divide this term by 2 times t subtotal, the 2's will cancel out to leave this, one of them is going to cancel out to leave behind this. Okay, so what I now do is times both sides by g. Okay, so if I multiply this term by g, the g's are going to cancel, and then I get a g times t subtotal over 2, which is this term here. And then I divide both sides by sine theta, which is the same thing as multiplying everything here by 1 over sine theta. And this is our equation for v sub 0 here. Okay, so let's find the maximum range. So remember that was our time of flight from this point down to this point down here. So to find the maximum range, all we do is just multiply the time by the horizontal velocity. Okay, so that is going to be v sub x equals v sub 0x, which is v sub 0 times cos theta. Okay, so we want the velocity in the x direction. Multiply that by t sub total, which was this time here, and we'll get the maximum range. Okay, so r sub max. So if we substitute that in, we get that equation there. And now the maximum height of the projectile. Okay, so remember y max was this, and then we just add y sub 0 onto that because it started off from height y sub 0. So that is the maximum height of the projectile y sub max. Okay, so let's have a look at projectiles on an incline. So what I've got here is my xy coordinate axis. So there's my y-axis here and my x-axis there. And what I've done is just inclined that through an angle of beta, where beta is measured from this horizontal line here I'm calling x prime. And I've also got a new vertical line I'm calling y prime. And the angle theta is still measured from v sub 0 and the x-axis. So that hasn't changed. But the only thing that has changed now is just the xy coordinate axis has been rotated through an angle of beta. So when the particle is launched, it's going to follow this path. Okay, so you can kind of imagine the particle was being fired from the bottom of a ramp, and then when it's fired it's going to hit the ramp some distance from where it was launched. So we're going to change notation now for the acceleration. So we're going to say the acceleration is going to be a sub y prime, which is minus g, which acts vertically. Okay, so the reason it's a sub y prime is because y prime here is our new vertical axis, and g is still minus 9.81 meters per second squared. Okay, so if we want to write the velocity of the projectile in each direction, we do it like this. So if we want to know the velocity in the x prime direction, we just do v sub 0 times cos of beta plus theta. So we add these two angles here to get the angle in between v sub 0 and the x prime axis. So that's going to be v sub 0 x prime. Okay, so that is the velocity in the x prime direction. And then if we want to find the velocity in the y prime direction, it's going to be v sub 0 times sine of beta plus theta. Okay, so that's going to be the velocity of the particle in this direction. And the velocity of the particle in the x and y direction is the same as before. So v sub 0 x is going to be v sub 0 times cos theta, and v sub 0 y is going to be v sub 0 times sine theta. So these are our equations for the velocity of the projectile in each direction. So in the x prime, y and x directions. So we need to find the acceleration in the x direction and the y direction. Because g is acting downwards, that means we can take the components of g in the x and y directions. Okay, so in the y direction we've got minus g times cos beta, and in the x direction we've got minus g sine beta. Okay, so notice that this angle and this angle are going to be the same. Okay, so that is our acceleration in the x direction, acceleration in the y direction. Acceleration g is only acting in the y prime direction this time. Okay, because y prime is our new coordinate axis in the vertical direction. So let's find the time of flight of the projectile. So if you remember this equation from earlier on, okay, so we're just going to set y is 0 because the displacement in the y direction is just going to be 0. And we're going to replace v sub 0 y with v sub 0 times sine theta, which is exactly what we had before. And I've replaced g there with this here. Okay, so g, so the acceleration in the y direction is just going to be minus g times cos beta. Okay, so I've just substituted this into there. Okay, so for this I have to use a quadratic formula to solve for t. So there's the quadratic formula there, and we're trying to solve for t, so x is going to match the t in this case. Okay, so we need to find what our coefficients would be. Our a coefficient is going to be this, and our b coefficient is going to be that. Okay, and c is just going to be 0, so I'm assuming you're already familiar with the quadratic formula. So because c is 0, this term is going to disappear, and the square root of b squared is just going to simplify down to b. So let's start off with subtraction. So if I just substitute b into here and substitute a into there, I'll get this. Then I can rewrite that like this, because minus 2 times a half is just going to simplify down to minus 1. And then that's going to simplify down to this. Minus is cancelled out to leave behind this. Okay, so there's our first solution. So now we're going to do addition. Okay, so if we substitute our values back in, so substitute b into here and here, substitute a into there, we get this. And then same as before, that's gonna simplify down to that, and this is going to become 0 on top, and we get t equals 0. So that's our other solution. So we've got these two solutions, and obviously we're going to take this one here as our flight time. So now let's find the range r. Okay, so we've got the range here r. So first I'm actually going to find x prime. I'm going to find the distance x prime where the particle hits the x-axis after its flight. So x prime is going to be v sub 0 x prime, which is the velocity in the x prime direction, times t. Okay, so that's just velocity times time, which gives us distance. And the distance in this case is x prime. So substitute v sub 0 x prime into there from here. Okay, so I just substituted that into there. And then I can substitute the flight time into here as well to get that. And then that's going to give me this. And then I can rewrite that like this. Okay, because I've got a v sub 0 there times a v sub 0, which gives me v sub 0 squared. And 2 is being multiplied by all of this. So that's why I can just put 2 there. So now I can find r. So just applying trigonometry. In this case, this is going to be the adjacent. So x prime is the adjacent. And the angle in between is beta. So I'm just applying trigonometry here. So r is going to be the hypotenuse. So then I'll substitute in x prime. So remember we found x prime here. So I'm just substituting that into here to get this. So this is what I found so far. So next I'm going to find y prime. So I'm going to find the vertical distance the projectile has travelled at the end of its flight, y prime. Okay, and again applying trigonometry. It's just going to give me this. Okay, substitute r into there to get that. So next I'm going to find y max, which is its maximum y distance. Okay, so that will be at the center of its motion there. Okay, so I'm going to use these two equations in the y direction. So the velocity in the y direction is v sub 0 times sine theta, and the acceleration in the y direction is minus g times cos beta. Okay, which is here. So I'm going to apply this equation now. So the velocity is 0 at max height, and at the initial position y sub 0 is also 0. So initially y was 0, and when it's at the maximum height here, it's going to be, the velocity is going to be 0 in the y direction. Okay, so I'm going to set v sub y to 0, and I'm going to set y sub 0 to 0 to leave behind this, and I've just rewritten y as y sub max. And then subtract that from both sides, and then substitute my values in. So I've substituted v sub 0 y into here, and I've substituted a sub y into g. And then I can divide both sides by minus 2g cos beta to get this. And then the minuses cancel out, leaving behind this, and that is my height, y sub max. Okay, so this height here. So if I look at the projectile being launched down the incline this time, my equations change to this. Okay, so v sub 0 x prime is just going to be v sub 0 times cos theta. Okay, so this is theta here. And to get the velocity in the x prime direction, it's just v sub 0 times cos theta. And the velocity in the y direction is going to be v sub 0 y, which is v sub 0 times sine theta plus beta. So if I do the same thing again, but using these equations, I get these equations this time. Okay, so if we compare that to the equations up the incline, so you can either go through that yourself and double check this, or you can just take my word for it. So if you're not already familiar with these equations, I would just write these down now. Okay, so write them down on a bit of paper, and also write down these equations that we found earlier on. So we found an equation for the flight time of the projectile for this situation here. We found the maximum y distance, and we found the maximum range as well. And we also found flight time, maximum range, and maximum y distance for this situation when the projectile is being launched from a height y sub 0. Okay, so write these down too, so that you have something to take away from this video. So now we're going to determine what angle theta would give the maximum range for this projectile along this incline. So this is quite a lengthy process, but we're going to go through this. So first I'm going to say the angle del. Okay, so the symbol there, del, I'm going to say that is equal to theta plus beta. Okay, so I've just simplified things down a bit there by just saying the angle between v sub 0 and the x prime axis here is just del, where del is equal to beta plus theta. And I'm going to say x prime is equal to the velocity in the x prime direction times the time of flight. Okay, so remember we got this from earlier on. The velocity in the x prime direction is just going to be v sub 0 times cos del, or cos beta plus theta. So I can simplify it down like this. And then I can say r cos beta is equal to v sub 0 times cos del times t. Okay, so this time I'm just rewriting x prime as just r cos beta using trigonometry. Where r is the hypotenuse there and x prime is the adjacent, I can use trig identities to rewrite x prime like this. And then if I divide both sides by v sub 0 times cos del, I get an expression for t. So now I can use this equation here in the y prime direction. So I can say y prime equals v sub 0 times sine del times t minus half gt squared. Okay, so that is in the y prime direction. And then I can substitute y prime with r times sine beta. So again using trigonometry. And then what I can do is substitute t into here and here to get this expression there. Okay, so if I bring this equation down here now, so if I divide everything there by r, this r is going to cancel, this r is going to cancel, and we're going to lose an r on top here. So we're going to be left with this. And then what I can do is rewrite sine del over cos del as tan del, and v sub 0 there and v sub 0 there will cancel out, leaving behind this expression. And then if I divide both sides by cos beta, okay, so I'm dividing both sides by cos beta to get sine beta over cos beta, that cos beta there is going to cancel out, and I'm going to get a cos beta on top there cancelling out. So I can rewrite sine beta over cos beta as tan beta, and if I add this whole term here onto this side, I get this. So I just added 1/2 times g times r cos beta over v sub 0 squared times cos squared del. Okay, so I just added that term onto this side to get this. Okay, so let's continue on. Okay, so now I just subtracted tan beta from both sides to get this. And then I multiplied both sides by 2, and then multiplied both sides by v sub 0 squared times cos squared del to get this. So I just multiply both sides by this bottom term here and by 2, so that this half goes and we get an extra 2 on this side as well. And then if I divide both sides by g times cos beta, okay, so I just divided both sides by g times cos beta to get this equation here. Next I want to take the derivative of r with respect to del and set to 0, okay, since we're trying to find the maxima of the function. Okay, so we have a function here where r is a function of del. Okay, so r, the maximum range along the incline, is going to vary with del. And I've got r here as a function of del, so if I find the derivative and set it to 0, I can find the maxima of the function. So I can find what angle del would give me maximum range. Okay, so if we bring this up there, and then I'm going to say a equals 2 times v sub 0 squared over g times cos beta, and I'm going to say b equals tan beta. So that means if I make these substitutions into that equation, I'll end up with this. Okay, so a was just equal to all of this, and b down here was just equal to tan beta. And I did that just to simplify it down because beta and v sub 0 are constants, okay, and so is g. These are all constants, so that means I can put them all together and put them under a constant term. Okay, since I've got two functions here of del and they're being multiplied together, I'd have to use the product rule. Okay, so there's the product rule, so dr by d del of u times v is going to be u prime times v plus u times v prime, and I'm setting u as a times cos squared del. Okay, so I'm calling this term here u, and then if I take its derivative I get this, and then if I set v as tan del minus b and then take its derivative to get v prime, I get 1 over cos squared del. Okay, so if I substitute u into here, u prime into there, v into here, and v prime into there, I'll end up with this equation down here. Okay, so I just substitute the values u, u prime, v prime into here to get this. And this is our derivative. So what I can do now is simplify this down a bit. So cos squared del over cos squared del, that's going to cancel out. Okay, so that's just going to give me 1. And then if I redistribute that minus sign there, these two terms are going to swap over like this. And then if I factor out a from both terms, so I've got an a in this term here and just an a there, I can factor out the a to get this expression. Okay, so that is our derivative now, and what I'm going to do is set that to 0. Okay, so I've just set the derivative now equal to 0, and I'm trying to find what angle would give me maximum range. So from this, because I've got a times this lot here and being equal to 0, therefore I can say a equals 0 and this term equals 0 as well. So we're only interested in this term because it's got a del in it, and that's what we're trying to find. So we're not interested in a, we're only going to take this term. Okay, so now remember a was this and b was that. So we no longer have an a term in here, so we've got no use for this, but we do still have a b term there. So if we substitute b back into here, we get this. And then I can rewrite tan del as sine del over cos del. And then if I multiply out the brackets, I get this. Okay, so I just multiply the brackets out. So I've done this times tan beta and this times all of this lot there to get this. So cos del over cos del is going to be 1, and I've got sine del times sine del to get sine squared del. And then I can rewrite 2 times sine del times cos del as just sine 2 del using trig identities, and I can write sine squared del like this. Okay, so again using trig identities there. Then if I expand the brackets with 2 there, so if I do 2 times minus a half, I'm going to get minus 1 here, and then minus 2 times minus a half there is going to give me plus cos 2 del, and I'm going to be left with plus 1 at the end. And then I've got minus 1 there and plus 1 there, so they're going to cancel out to leave behind this. And then if I subtract cos 2 del from both sides, and then if I divide both sides by tan beta, I get this. And then if I divide both sides by cos 2 del, I get this over here. And then I can rewrite this as tan 2 del, which is equal to minus 1 over tan beta. If I take the inverse tan of both sides, I end up with this equation here. So now I can simplify this down. Okay, so bring our diagram back there. Okay, so I'm just going to label some angles on this diagram here. So I'm going to say the angle between R and Y prime is alpha. And I'm going to say the angle between this horizontal line and R is beta. Okay, so beta is equal to this angle here. And then I can rewrite this as 2 del equals inverse tan of minus cotangent of beta, because 1 over tan beta is cotangent beta. And then I can say from this beta equals 90 minus alpha from this diagram. So it's 90 degrees between this horizontal line and Y prime. Okay, and if I want to find beta, I'll just do 90 minus alpha to get beta. And then if I rearrange that for alpha, I get alpha equals 90 minus beta. And then I can say tan alpha equals x prime over y prime. So x prime there is the opposite and y prime is the adjacent. So I can say tan alpha equals x prime over y prime. And I can say tan beta equals y prime over x prime. Okay, so again using trigonometry here. So here's our angle beta, y prime is the opposite, and x prime is the adjacent. So I can say tan beta equals y prime over x prime. And then I can say 1 over tan beta equals x prime over y prime. So I've just flipped this over. And because I know tan alpha equals x prime over y prime, and 1 over tan beta equals x prime over y prime, I can say 1 over tan beta equals tan alpha. Okay? And I can rewrite this as cotangent beta, and then I can substitute alpha into there. So if I substitute alpha into here, I get 90 minus beta, because remember alpha here was 90 minus beta. And I want to multiply it by minus 1, because this matches the original equation, because we've got a minus cotangent there. That doesn't really change anything. The only difference is that it's just going to be minus, okay? And then if I take the inverse tan of both sides of this equation, I get this. So inverse tan of minus cotangent beta equals inverse tan of minus tan of 90 minus beta. So I've got inverse tan of tan, they're going to cancel out to leave behind this. And now notice that I've got inverse tan of minus cotangent beta equals minus 90 minus beta. So we can say also that inverse tan of cotangent equals 90 plus beta. Okay, so this doesn't make any difference whether it's negative or positive. The only difference is that you get a positive value this time. And therefore we can say 2 del equals 90 plus beta. So we'll put that equation here. And then if I divide both sides by 2, I get this. And remember, del was equal to beta plus theta. So if I substitute that back into there, I get this. So I can say theta equals 90 plus beta over 2 minus beta. Okay, so that is the angle that will give us the maximum range on the incline. Okay, so hopefully that made sense to you. So this is the angle that would give us the maximum range along this incline. Okay, and then if we was to repeat the same thing again, so everything we just did there, if we repeat that again, but this time using these equations from the beginning, so saying r cos beta, okay, is going to be v sub 0 times cos theta. So that is the velocity in the x prime direction times time. Okay, so if you remember from the beginning we started off with this, but this time we're saying the velocity in the x prime direction is equal to v sub 0 times cos theta, where before it was v sub 0 times cos theta plus beta. So if you repeat the derivation again, you'll get this time. So this is the maximum range of the projectile, but this time being launched down the incline. Okay, so you might want to jot these down. Okay, so add this to your notes, as this could be useful at some point. Okay, so now we've completed our introduction to curvilinear motion and the rectangular coordinate system. We've looked at projectiles and got all the equations that we need. Now we're going to complete 3 example problems. So example 1. A projectile was launched at an angle of 40 degrees to the horizontal at a speed of v sub 0 equals 100 meters per second. Find A, the time of flight, okay, B, the horizontal distance covered by the projectile, C, the maximum height reached by the projectile. Okay, so we're literally just going to apply those equations. Okay, so we're going to apply this equation now, so v sub y equals v sub 0 times cos theta minus gt. Okay, so we just substitute our values in, and we say v sub y is going to be 0 up to this point here. Okay, so v sub 0 was 100 meters per second, theta was 40 degrees, g was minus 9.81 meters per second squared, and t we don't know. That's what we're trying to find. So I'll just subtract both sides by 100 times sine 40 to get this. Divide both sides by 9.81 meters per second squared to get that. And then the minuses cancel out, leaving 6.55 seconds. So because that's the time taken to go from here to the central point there, so at maximum y distance, that's only half of the flight time. So we multiply that by 2 to get 13.1 seconds. Or we could have used that equation that we got earlier on. It would have actually been simpler to use this equation, because I think taking this route to solve this problem, you're more likely to make a mistake. But if you have this equation memorized, all you do is just substitute the values in. Okay, so I'll just substitute those values in and I get the same answer, which is 13.1 seconds. So now we're going to find the horizontal distance covered by the projectile. Okay, so v sub x equals v sub 0x, okay, which is v sub 0 times cos theta. And that means we can say v sub x equals v sub 0 times cos theta. And because I know the overall time of flight, I can find the x distance, which is the maximum range r. So I can say x equals 100 times cos 40 times 13.1, remembering that our time was 13.1 seconds. So this is just velocity times time to get distance. Put that in, I get 1003.52 meters. Okay, and that's our answer. So C, the maximum height reached by the projectile. So I can say Vy equals V sub 0 times sine theta. And I can use this equation here. So y equals V sub 0 plus V sub 0 y times t minus half gt squared. So I'm going to say V sub 0 is 0 because it started off from y position 0. And then I'll substitute V sub 0 y with this. Okay, so I'll substitute that into there to get this. Substitute all my values in. So I knew what theta was. I knew what V sub 0 was, which was 100. I knew what theta was. I know the time of flight to go from this point to that point. I know the acceleration due to gravity. And again, I know the time there. So I substituted all those in. And then 100 times sine 40 times 6.55 seconds gives me 421 meters. And then 1/2 times 9.81 times 6.55 squared gives me 210.44. And then find the difference, I get 210.6 meters. But if I apply this equation that we derived earlier on, and then substitute those numbers in, I'd end up with the same answer. So example 2. A marble the initial speed of v sub 0 equals 100 meters per second and hits the floor 5 seconds later. Find the distance the table is from the floor. B, the horizontal distance covered by the marble. C, the magnitude of velocity when the marble hits the floor. So we're going to apply this equation now in the y direction. Okay, and that is our y distance there from the tabletop to the ground. And then if we substitute our values in, so we knew y sub 0 is 0, and we knew v sub 0 y initially is going to be 0 meters per second. Okay, so in the y direction initially it was 0 meters per second. We know the time of flight was 5 seconds. And notice this time I've got positive g. Okay, so this time g is positive because it's accelerating downwards. And again, I know the time of flight there. So if I put all that into my calculator, I get 122.63 meters. Okay, so there's my x distance there, so the horizontal distance covered by the marble. So I can say v sub x equals v sub 0x equals 100 meters per second, because when it's released with 100 meters per second in the horizontal direction, that's going to remain 100 meters per second in the horizontal direction until it hits the floor. I can just apply this equation now, which is just x distance equals velocity in the x direction times time. Okay, so I knew that velocity in the x direction was 100 meters per second, and I knew the time of flight was 5 seconds. So multiply them, I get 500 meters. Okay, so x is 500 meters. So now we'll find the magnitude of velocity when the marble hits the floor. So we knew our y distance when the marble hit the floor, and we knew our x distance when the marble hit the floor. Okay, so we're going to apply this equation now. Okay, so you should be familiar with this. Again, g this time is being put as positive because the marble is accelerating. This term is going to disappear, leaving behind this. And we also knew that y sub 0 was 0, so that goes as well. So that just leaves us with this. Okay, so take the square root of both sides to get that. Substitute our numbers in. So we substitute g and y into there. So remember y was 122.63 meters, which I've just put into there. That simplifies down to square root of 2406, which gives us 49 meters per second. Okay, so that is the velocity in the y direction when the marble hits the floor. We also knew that the velocity in the x direction was 100 meters per second, so v sub 0x equals v sub x. Okay, so the initial velocity in the x direction equals the final velocity in the x direction, which is 100 meters per second because it's constant, remember? And then if we take v sub x and v sub y, apply Pythagoras to that, we end up with v equals 111.36 meters per second. Okay, so that is the magnitude of velocity when the marble hits the floor. Example 3. A ball is launched upwards on an inclined ramp with an initial velocity of v sub 0 equals 75 meters per second. The ramp has an incline of 15 degrees to the horizontal. Find A, the angle the ball should be launched with to the ramp for the maximum range. B, the vertical distance the ball has risen after impact. C, the time of flight. Okay, so remember this equation from earlier on for the angle theta that gives us maximum range when being launched up an incline. This was our equation, and remember beta is the angle of incline, which is our range. Okay, so we want to know what angle do we have to position that particle when it's launched with 75 meters per second to get the maximum range. Okay, so we substitute our numbers in. So we knew beta was 15 degrees, so substitute that in to get this. Okay, that simplifies down to this because 90 plus 15 is going to give us 105. That simplifies down to that, and so we get theta equals 37.5 degrees. So that is the angle that will give us the maximum range. So now we want to find y prime. Okay, so remember y prime was that distance there. So that is the vertical distance the ball has travelled after impact, and our equation for that was this. Okay, so if we just apply this equation now, put our numbers in, okay, simplify all that down like this. After all our simplifications, we end up with 118.1 meters. So now we want to find time. So if you remember, this was the equation we got for the flight time when being launched up the incline. So again, substitute our numbers in. So we knew theta was 37.5 degrees from the previous question. We knew beta was 15 degrees, which was given to us here. And we knew v sub 0 was 75 meters per second. So if you multiply that by 2, you'll get 150. Simplify all that down. Okay, so the top there is 91.31 over 9.476, which will give us 9.64 seconds. Okay, and that's our answer for part C. Okay, so if you found this video helpful and you would like to practice some more questions, then click onto the link in the video description, or you can just copy and paste it directly into your search engine, like so. Okay, and then you'll take them to the home page here. So if you click on courses, engineering dynamics, so this is the main home page here. So you've got your formula sheet here, which summarizes this lesson. Okay, so projectile motion. So these are all the equations that we discussed in the video. So they're all summarized here for you to use. And then if you click on rectangular coordinates and projectile motion, so that's what this video was. So if you click onto that, the same video is available here. Okay, and you've got these practice questions here for you to complete. Okay, so these are all the questions. So question 2.1, 2.2, and so on. Okay, so the answers are shown at the end. So these are all the answers. And then you've got the course content here as well, so these are videos for each individual question. So you can watch them at will once you have made the purchase. So if you want to apply what you just learned, here's the place to do it.